All right, for the rest of the day today, what I want to do is I want to go through the reading content of sections 4.1, 4.2, and maybe a bit in 4.3 to emphasize factual information that you should know for exam 3 and for use on homework. And as we go through that content, I'm going to talk also about the end of chapter 3, which involves some theorems, including something called the mean value theorem. So we've done some problem solving, certainly last Friday, a little bit today with this project. Let's now focus on factual information. This is going to be kind of theoretical, but it's important to really pay attention to. So first of all, we've got some definitions and facts in section 4.1. Okay, and I'll probably draw some examples as we talk about this content. Focus less on formulas and more on drawings. The drawings help you understand the concepts better than the formulas do. So the first definitions to look at are definitions of local minimum and local maximum. Suppose we got a point P in a domain of a function f. So it's understood that P is a point, a number, really. P, even though they say point, they really mean number. Sometimes we use the word point to refer to number. In the domain of f, what's the domain of f? Well, it could be the entire real number line. Could be an open interval that does not contain its endpoints. Could even be a closed interval that does contain its endpoints. And actually, you could even get more abstract than that, but we won't. F has a local minimum at P. Remember, P is a number. If f of P is less than or equal to the values of f for points near P. And a similar kind of thing for a local maximum. If f of P is greater than or equal to the values of f for points near P. Now, as definitions, this is actually not precise enough for most mathematicians, but it will be good enough for us if we think about pictures. For example, what does it mean to be near P? That word near is kind of vague. Well, let me just give you the basic visual idea. So here's the x-axis, say. That's our domain. Maybe the entire real number line. And say I've got a function that looks like this. Actually, let's make the domain be a closed interval. Let's call this number A and this number B. And the domain of this function is the closed interval from A to B. In interval notation, that's written like this, with square brackets to indicate to include the endpoints in the domain. At what points do we have local minimum points? Well, it should make sense that we have a local minimum point right there. In fact, that would be also a global minimum point. For all x values in this domain, this closed interval from A to B, f of A is as small as possible. F of A is the second coordinate of that point. For this domain in this particular graph that I drew, there's no way the function outputs get lower because the graph doesn't go below that point. So we would say f of A is both a local and global, in fact, minimum value of f over this interval from A to B, this closed interval where I include the endpoints. If I had decided not to include the endpoints in my domain, listen carefully, if I had decided not to include the endpoints, then actually f of A would not be a global minimum value or a local minimum value. Why? If I had decided not to include the endpoints, which I could have decided to do. You want to say? You're getting warm. If the endpoint is not part of the domain, if I do not include a in the domain here, then the function actually never reaches this value at f of a. This point would not be part of the graph. It would get close to f of a, in fact, arbitrarily close to f of a. And in fact, you would say the left-hand limit of the function as x approaches a is this number, whatever that number happens to be. But it would not be a function output if I did not allow a to be in the domain, which again, I could do. I could decide not to allow a to be in the domain. That comes up in practical problems sometimes, and it comes up in the abstract here. I'm talking in the abstract at the moment. I could have decided to not include a in the domain, and therefore f of a would not even be defined, so it can't possibly be the lowest value. Although, again, this limit would exist, there'd be a limiting value, whatever that second coordinate of that point is. Local means nearby. For points near a, this is as small as the function gets. Local means f of a is less than or equal to f of x when x is close to a. To a. Global means, in fact, f of a is less than or equal to f of x, not just near a, but for all x in the domain. For all x in this closed interval, not just when it's close to a. But that's not the only place to have a local minimum. There's another local minimum where this function has a low point, like a valley here. It's like the bottom of a bowl, right there. We call that P1. There's going to be a P2, by the way, as well, and P2 is actually going to be less than P1, but f of P1 is a local minimum value of f. I'm not going to say over the interval from a to b. The global back here really refers to the entire interval. I'm just going to say it's a local minimum value of f. In other words, f of P1 is less than or equal to f of x when x is close to P1. How close? Well, close enough that you don't get close to these outputs over here that are lower than f of P1. F of P1 is about here. If I went far enough from P1, in other words, close enough to A to make the outputs lower than f of P1, then those are the points that are not close enough to P1. The answer for how close to P1 depends on the function. It depends on the graph. If you are worried about trying to see what happens over here, you can just focus on some little tiny interval around P1 and say, yeah, for these inputs, the outputs of the function never get lower than f of P1. The graph is concave up there, for example. And you've got, hey, P1 is a critical point. Look at that. F prime of P1 is 0. It's not an accident. So it has a local minimum value of f, but it's not a global minimum value. But f of P1 is not a global min value of f over the interval, over its domain. Why? Because f of a gets lower, or even f of x when x is really close to a gets lower than f of P1. I'm not going to write it out in words, but there's a global maximum, both a global and local maximum at B. And that global maximum value is f of B. And there's a local maximum, but not global maximum at this point. Call that P2 f of P2 is higher than f of x when x is close to P2. Don't be bothered by the fact that I made P1 to the right of P2. It's not a big deal. And again, notice that these ones that are local but not global, and that are more importantly not endpoints, the derivative is 0. Those are critical points of the function. At the endpoints, they're actually not critical points because the slope is not 0 there and not undefined, though you might argue the slope is only one-sided. We won't get into such technical details. By the way, I didn't have to make global max and global min at A and B. I could have made it so that the global max and min occurred at P1 and P2. I could have drawn the graph, say, more like this. Then these points would be both local and global, maxes, min and max. So I could have drawn it like that. Paying attention is really, really key. If you want to do well on exam 3, including true, false, multiple choice questions, I always give questions related to these kinds of concepts. Thinking about these pictures as well as thinking about your homework assignment will reinforce the concepts. We've already talked about this definition. A point P in the domain where either f prime of P is 0 or f prime of P is undefined is called a critical point. We talked about that last Friday. Sometimes we call the point itself on the graph also a critical point. So again, the word point is being used with ambiguity here. Sometimes it means the x coordinate, sometimes it means the actual point on the graph. That is a somewhat standard thing to do, is be kind of ambiguous here and use the word point in either situation. However, when you see the word critical value, that means output. In fact, when you see the word minimum value or maximum value, that also means output. Write that down. Values always refer to outputs. When I say, like on exam 3, I'll probably give you a problem and say, find the global minimum or maximum values. I mean function outputs, y coordinates, second coordinates if you prefer. Values refers to outputs. Why are critical points important? Because they are where local extrema are guaranteed to occur. Or that's maybe not the best way to say it. If you have a local extrema, it's guaranteed to occur at a critical point. That's the better way to say it. This theorem says if you've got a local max or a local min at this point, and again, the word point here is referring to just the x coordinate, a number, which is not an endpoint in the interval because these endpoints kind of give us trouble, so to speak, because the slope doesn't have to be 0 at the endpoints. If f is differentiable at a, meaning it's got a derivative, then f prime of a must be 0. If f is not, in other words, a must be a critical point. If f is not differentiable at a, then a is also a critical point. Say it again. When you're talking about local maxes and mins that are not endpoints, so it's the top of a hill or the bottom of a valley, if f has a derivative at a, then the derivative must be 0. And if f is not differentiable at a, that means a is a critical point as well. So either way, whether f is differentiable or not at a, you've got a critical point. Which also means if you're not at a critical point for the function, then f can't have a local max or min there if you're not at a critical point and also not at an endpoint. If you're not at a critical point and not at an endpoint of the interval, if the function, for example, is increasing near a, then you can't have a local max or min at a, right? That makes intuitive sense just looking at the picture. Effectively, there's two ways local maxes and mins can occur at critical points. You either have a top of a smooth hill where the slope is 0, or you might have like a corner in the graph where the slope is undefined. Either case, you're at the top of a small mountaintop, right? You pretend these are mountains or hills. For valleys, for minima, you're either at the bottom of a bowl, a valley with a 0 slope, or maybe the function's not differentiable there. Either way, you're at a critical point. You're at a place where the derivative is either 0 or undefined when you've got local maxes and mins, and you're not at endpoints. At endpoints, well, you don't have to have a 0 slope, and these can be at least left or right differentiable. This one would be differentiable from the right because you're talking about tangent lines that come in this way. It's a left endpoint. This one would be differentiable from the left. Don't worry about differentiability from the left and right so much. Just focus on the fact that, hey, we've got both local and minima and maxima at these 2 points. Local min and global min at this point, local max and global max at this point. And the slope as you approach those points is not 0. And does seem, these are nice smooth curves that it seems to still be defined. You can't, again, expect to remember this kind of stuff unless you think about it consistently. Not just for homework. And when you do the homework, don't rush. I know we want to rush, we got other things to do, but give yourself enough time that you can spend time not only checking your answers, but thinking about whether they make sense and thinking about what your answers mean and the graphs mean in terms of these concepts. Rethink about this stuff when you work on the homework problems. It'll be so beneficial. And it'll be beneficial in terms of time as well, because you'll understand the content better. And that means you'll be able to solve problems in the future more quickly. And you'll do better on tests. You won't have to study as much for tests. You won't have to cram as much if you think about things more consistently. Big word of warning, though. Just because a function has a critical point at some value of x doesn't mean you're guaranteed to have a max or min there. Say that again. Just because you're at a critical point where the derivative is 0 or is undefined doesn't mean f actually has a max or min there. And the simplest example that you should know for exam 3, that if you look at old exam 2s, I actually put out on at least one of those old exam 2s, is this function f of x equals x cubed over any interval that contains the number 0, say. I'll emphasize an open interval. Over any open interval containing 0, x equals 0, this function does have a critical point at 0. F prime of x is 3x squared. If I set that equal to 0 and solve for x, obviously x must be 0. Very easy equation to solve. This is the only critical point of f. However, it is not a place where f has a local max or local min over your open interval containing 0. Say your interval is this interval here. That's the interval, that's the domain that I'm thinking about. The graph of the function x cubed, I'm not including the endpoints here, looks about like this. The open circles is just emphasizing I'm not including the endpoints. It's not that points are as big as circles, okay? Don't think that. Points have no area to them. They are smaller than atoms. They are smaller than electrons. though okay, I don't want to get into quantum mechanics. All right, don't misunderstand that. I'm just emphasizing that the endpoints are not a part of the domain. So the global min and global max actually don't exist for this function on this domain because the function never reaches that point and the function never reaches that point. It gets arbitrarily close to them, but not to the point itself. Kind of a subtle concept. X equals 0 is a critical point. The slope does exist here, and in fact is 0. The tangent line is horizontal. However, that's definitely not a local min or a local max. It's not the top of a small hill or the bottom of a small valley. In fact, even though the tangent line is horizontal there, the function itself is never horizontal, which is a weird thing to wrap your mind around. If you zoom in closer and closer to the origin here, this purple graph will look more and more horizontal until you can't tell the difference. It will look like, if you're close enough to the origin, it will look like it is the x-axis. But technically speaking, it's not. The only spot this function equals 0 is when x is exactly 0. If x is 0.000001, x cubed is, well, 10 to the negative 21. Very, very close to 0, but not equal to 0. That's not calculator error. That's accurate. 10 to the negative 7 cubed is 10 to the negative 21. 10 to the negative 100 cubed is 10 to the negative 300. The function only equals 0 exactly when x is 0 exactly. But it gets so close to 0 when you zoom in far enough that you can't tell the difference between the x-axis and the graph of this function. That's why the tangent line is horizontal, but it doesn't have a local max or local min there. It doesn't look like the top of a little hill or the bottom of a little valley. So that's a critical point that's neither a local max nor a local min. Well, doesn't that contradict this theorem? Doesn't that contradict it? If f is differentiable with a local max or min, the derivative must be 0? No, it doesn't. Because this theorem is not both ways. It does not say if the derivative is 0 and you're not at an endpoint, then the function must have a local max or min there. The if-then statement is a one-way implication. If it's at a local max or min and you're differentiable, then the derivative is 0, not the other way around. Derivatives can be 0 at points that are not local maxes or mins. So we need some other test to know whether we're at a local max or a min. There's two of them. One is called the first derivative test, and the other is called the second derivative test. And last Friday in our examples, we were really using the first and second derivative tests, and I even mentioned them, I think, without looking at these boxes in the book. The first derivative test says, suppose you're at a critical point of a continuous function, and it's in this description of moving from left to right, that means as x increases, it's really implicit that P is actually not an endpoint of the domain. They don't say it there. But really, P is not an endpoint. You might want to write that along the side or something. P is not an endpoint of the domain here. It's sort of implicit in the fact that you're thinking about x increasing through the critical point as you move left to right along a number line. If f prime changes from negative to positive, then f has a local min. If f prime changes from positive to negative, then f has a local max. So it probably would be more ideal if they also made one extra assumption here, that f prime itself is also continuous. They don't state that, but that does keep things simpler. We're not going to worry about that though. Think about it with a picture. If f prime changes from negative to positive at P, meaning if we make a number line like we did last Friday, and P is a critical point, And f prime, if we're talking about its sign of f prime, remember when I did this kind of thing? Changes from negative to positive if as x increases through p, as you imagine x moving from left to right. Then f itself changes from in direction from decreasing to increasing as you increase through p. In other words, at p, you've got to have a low point. And if f prime of p exists, the graph will look like part of a smile and a low point at p. There's a local min there. If we flip it around and f prime changes from positive to negative at p, positive to negative as x increases through p, that means f changes from increasing to decreasing as you cross through p. It's got to be a local max there. You look like part of a frown, and at p, you're at the top of a little hill. To prove this first derivative test, you need something, a theorem from section 3.10. Last section of chapter 3, a very theoretical section, even more theoretical than what I'm showing you here. I'm going to hold off on talking about that for the moment. Sticking with me here? You feeling awake enough? These pictures are key to understanding the reading. And you should strive to not only do the problems, but also understand the reading. I didn't have my book with me today, so I'm borrowing pages of the book from somebody else here. Trying to find my way through these pages. If there's a first derivative test, there must be some other kind of test. Yes, it's called the second derivative test. Both tests are to use to find local maxes and mins. They both do the same thing. You do not need to use them both, however. It's good enough to use one or the other. Sometimes one might be easier to use than the other. And so based on the problem, you decide which one to use, first derivative test or second derivative test, based on which one seems easier to use. If the second derivative is easy to find quickly, probably the second derivative test is easier than the first derivative test. Because with the first derivative test, you got to make those number lines and you got to think about the sign, positive or negative, of the first derivative on intervals. Whereas with the second derivative test, you are testing the sign of the second derivative, but just at one point rather than over entire intervals. So you don't have to make number lines. That's kind of nice. The second derivative test says, well, it's implicitly assuming f double prime exists here. And also without telling you, in the nicest situation, f double prime is also a continuous function here, but our book is not being very precise. It's just trying to give you the basic idea. Notice in all three bullet points, we're assuming f prime of p is 0. We're assuming we're at a critical point, and it's also implicit in this that probably p is not the endpoint of the domain of the interval. If we've got a closed interval as the domain, it's not one of the endpoints. If f double prime is positive, then f has a local min. If f double prime is negative, then f has a local max, which is a little confusing. Negative at a min and positive, or positive at a min and negative at a max, shouldn't it be the other way around? It's not. I'll explain why in a second. If f double prime of 0 is 0 at the critical point, then the test tells us nothing. It might be a local max, it might be a local min, it might be neither. In fact, the second derivative test does tell us nothing in this example. If I take the second derivative, f double prime of x, and get 6x, if I plug in my critical point into that, I get 6 times 0, I get 0. The second derivative test tells you nothing. That's the case where it tells you nothing. And in fact, 0 is not a local max or a local min of this function on some open interval containing 0. Why do I keep saying open interval containing 0? Well, technically, you could have a local min or local max at 0 if 0 was the endpoint of the domain. I'll let you think about that. If it's not the endpoint, and if the domain is an open interval with 0 inside of it, then it's not going to be a local max or a local min for this function. I claim these first two bullet points are correct, but they're confusing. Think about them. F double prime is positive. What does that mean about F? What does positive second derivative over some interval mean about F in its graph? I'm looking for two words. The first starts with C and the second starts with U. The graph is concave up. Looks like a smile. Hey, it's a low point. If F double prime is negative, then the graph is concave down near P. Yeah, I'm implicitly assuming F double prime is continuous as well when I say that. Looks like a frown. You got a high point near P. I am assuming F prime of P is 0. I am assuming I have a horizontal tangent at P in both cases. That needs to be checked first. You do plug in critical points into F double prime, not any old point. Take a breath. Inflection points. What is an inflection point? It's where F double prime changes sign. Not just where F double prime is 0, but where it changes sign. From negative to positive or positive to negative and vice versa. Or I guess I already said the vice versa. Here are your typical kinds of inflection points. Here the graph of F is concave up, so F double prime is positive. Here the graph of F is concave down, so F double prime is negative. F double prime is changing sign from positive to negative as X increases through P here. That's an inflection point. That's not a local max or min, though. You can have inflection points at places that are not local maxes or mins. There's another kind that changes sign from negative to positive. Again, it's not a local max or local min. The graph of X cubed, my pages here. The graph of X cubed has an inflection point at the origin. F double prime is changing from negative to positive as X increases through 0. There's an inflection point there. It's also a critical point, but it's neither a local max nor a local min. Inflection points can occur at critical points, but they don't have to. They can also occur at other points, like these. You should also know this example, x to the fourth. X to the fourth, that's what this example is, see the formula? Has a graph that looks kind of like a parabola, but it is flatter than the graph of a parabola at 0. In fact, it's flat enough that the second derivative of this function at 0 is 0. It's so flat there. However, it's concave up on either side of 0. The second derivative does not change sign as x increases through 0. Therefore, this point is not an inflection point. More theory that's worth emphasizing here comes up in the next section. Your homework problems, you're going to have some from this next section. This includes a definition of global min and global max. I was talking about that, 30 minutes ago. P is a point in the domain of F. There's a global minimum at P if F of P is always less than or equal to all the values of F for all other points in the domain. And global maximum of P if F of P is greater than or equal to all the values of F for all other points in the domain. Coming back here, F of A is a global min. Global, because it's for all X in the entire domain. F of P1 was not a global min, because there are values of X in this domain close to A where F of X is lower than F of P1. There's something called the Extreme Value Theorem that says if you've got a continuous function in a closed interval, there's definitely a global max and a global min somewhere. That's nice to know. If your interval is closed from A to B, and notice this also means we're not going off to infinity, then definitely there's a highest point on the graph and a lowest point if F is also continuous. You might wonder how this might fail if F is not continuous. I will do examples, but not today. This leads to a procedure. This box on page 197 gives you a procedure for finding global min and global maxes. Test the candidates, which are either the critical points or the endpoints. Those are all the candidates. You got a continuous function on some closed interval. You can't emphasize enough that the interval has to be closed. It's finite, it doesn't go off to infinity, and it includes the endpoints. You see less than or equal to's instead of strict less than. The procedure to find the global max and global min is to first find the critical points, which is the same thing we do to find local maxes and local mins. Then test, evaluate the function at all the critical points and at the endpoints. The largest value is the global max and the smallest value is the global min of the continuous function on that interval. Might not be global max and min over some bigger interval, but if your interval is defined in this way, if that's your domain and you're not considering any other X values, then this procedure is guaranteed to work. Let's put it into practice. Okay, this is not a copy from my books. I'm not necessarily assigning the circle problems. But maybe we should do one of them anyway. How about let's go ahead and do number 5 here. Section 4.2. Number 5, the directions say, find the global maximum and minimum of the function on the closed interval. They didn't put the word values in there, but that's what they actually meant. If they say find the global max and global min, they actually mean find the global max and min values, in other words, outputs, like I emphasized 20 minutes ago. Second coordinates. They didn't put the word values in there, but they mean it. Though you can cover your behind if you also find the locations, the X values where those occur. You can find them both. And in fact, you have to find the X locations before you can find the values. F of X is X to the 4th minus 8X squared. But don't just look at the function, look at the interval. The interval is the closed interval from -3 to 1. I'm not considering any other X's. Why, you might ask? Well, it does come up in some practical applications that sometimes you have to restrict the domain. Not a problem if you want to graph this first. just to get an idea of what the answer is. That's allowed, but make sure you show your work as far as finding critical points and checking the function value at critical points and at the endpoints. So it's x to the fourth minus 8x squared. Careful about the interval, though. In the window, you got to pick whatever interval they give you, -3 to 1 in this case. What are the outputs? Maybe you don't know at first. I do notice that f of 0 is 0, so I definitely want to include 0. -10 to 10 is probably not such a bad idea to try here initially. Let's go ahead and graph it. Okay, there we're seeing most of the graph. The part we're missing is the part over here. Let's go down further in the y direction, maybe to -30, just to play it safe. There we go. There's the graph. Where's the highest point? Where's the lowest point? Looks like the highest point occurs at the left endpoint of the interval, and the lowest point occurs at this critical point. That's the way it looks. Let's do the algebra now to confirm the answer. Take the derivative. 4x cubed minus 16x. Set it equal to 0, or see where it's undefined. This is a polynomial, so it will always be defined. Solve for x. You can factor a 4x out. You're left with x squared minus 16 or minus 4 in the parentheses equals 0. So that means 4x equals 0 or x squared minus 4 equals 0, which means x equals 0 or x squared equals 4, and this means x is plus or minus 2. This fourth degree polynomial has 3 critical points. 0 and plus or minus 2. However, only 2 of those are in this interval. 0 and -2, not +2. This interval from -3 to 1 only contains 2 of the 3 critical points, not the third. -2 and 0 are the other critical points. That are the only critical points in this interval. You don't have to think about the positive one that's not in the interval. You can ignore a +2. I'm after global max and global min, not local max or local min. So because of that, I don't need to think about the first or second derivative tests. I only need to do what the book said to do. Evaluate the function at the critical points and at the endpoints. The largest value is the global max. The smallest value is the global min. They put the word values in there and there. They mean outputs. That's implicit again in the problem statement. So all you have to do is just make a little chart now of function values at the endpoints and at the critical points. These are the critical points in that interval, and these 2 things are the endpoints. Plug them into the function. You don't have to think about does the derivative change sign. You don't have to think about that. You don't have to think about the second derivative test either. If you plug in -3 into the function, we get -3 to the 4th minus 8 times -3 squared. -3 to the 4th is positive 81. Minus -3 squared is positive 9. 8 times 9 is 72. 81 minus 72 is 9. Plug in -2, you get -2 to the 4th. Plug it into the original function. Minus 8 times -2 squared. That's positive 16 minus 4 times 8. Minus 32 is -16. Plug in 0, get 0. Plug in 1, get -7. On this interval then, from -1 or -3 to 1, the global max occurs at the left endpoint, and the global min occurs at the right end, at the leftmost critical point. That's the global min. It's implicit that these are global max and global min values. I'm putting the word value in here. The book didn't say value, but they meant value. If you were asked where does the global max occur, you'd say at the left endpoint -3. And where does the global min occur? You'd say at the critical point -2. And again, that jives with what you see in the graph. The highest point is over here at the left endpoint. The lowest point is right there at -2, which is a critical point. That's not an endpoint. There is still a local min there and a local max there, in fact. And in fact, even a local min at the right endpoint. You can think about the first and second derivative test at these critical points that are not endpoints. You'll see that the first derivative here changes sign from negative to positive as x increases through -2, and the second derivative is positive there. And here you'll see the first derivative changes sign from positive to negative as x increases through 0. Also, the second derivative is negative. So you can use the first and second derivative test to confirm local maxes and local mins at these critical points that are not endpoints. But we didn't have to do that in this problem because they only asked for global max and global min values. Find the critical points, plug in both the critical points and the endpoints of the closed interval to do that. All right, have a good day.